Hi, and welcome back to the wonderful world of the scientific hypothesis. My name is Brad Alger. A couple of videos ago, I explained how finding necessary and sufficient conditions is an ideal but unattainable goal for science. We can often show that some condition, like water, is necessary for some phenomenon, like life on Earth. It is far harder, however, to show that some condition is truly necessary and sufficient for some other phenomenon. Water is obviously not sufficient for life. Life depends on nutrients and countless other things that we don't fully understand or even know about. Yet scientists often make the claim that they found the necessary and sufficient conditions for some phenomenon. In this video, we'll look into a simplified example where scientists erroneously made this claim. We'll consider what it is they probably really meant, and we'll see how they could have expressed themselves more accurately and clearly. Okay, misuse of necessary and sufficient in science. What can go wrong and how can we make things better? Let's just review the basic terms. A necessary condition is where one statement must be true for another to be true. A sufficient condition happens if one statement is true, then another must also be true. And finally, necessary and sufficient conditions is where each statement implies the other. Both are true or both are false. Now, previously, I showed this example of logically necessary and sufficient conditions. In the wild, all baby bears are born to mother bears, and therefore a baby bear implies the existence of a mother bear. And on the other hand, to be a mother, a bear must have given birth to a baby bear, so the existence of a mother bear implies there must be a baby bear, and therefore a baby bear is a necessary and sufficient evidence of a mother bear. Each one implies the other. But this is a simplified, logically abstract case that doesn't seem to have much to do with science. Here's an example of the misuse of the terms in experimental science. To make this explicit, let's consider the following experiment. We have a cell in the brain somewhere in the nervous system called a neuron, also called a nerve cell. And this cell has different parts that we should be familiar with. So the first is the cell body, the main part of the cell. Then there is a portion called the dendrites. These are branches where the signals come into the cell. There's another part called an axon, which is where the signals leave the cell and go on to another cell. Now here's another neuron, another nerve cell, and at this region here, the signal passes from one cell to the other cell. This is called a synapse, and the signal flow goes in this direction. Understanding how synapses work is of importance for understanding how information flows in the nervous system, but in particular, when you learn something, synapses in your brain get stronger. That is, signals pass through synapses more easily from one neuron to the next, and that was the topic of the investigation we're going to talk about. Here we've zoomed in on just the synaptic region. You can see that the synaptic strength is normal, and the synaptic signals flow from the presynaptic side to the postsynaptic side. In these experiments, the scientists wanted to test the hypothesis that an increase in postsynaptic calcium could somehow result in synaptic strengthening. The way they did the experiment was to increase calcium at the same time they activated the synapse. And they did this a number of times at a fairly slow rate of stimulation, and they found that, indeed, the synapses became stronger. This indicated then that increasing postsynaptic calcium does make synapses strong. But was the increasing calcium necessary to make synapses strong? To determine whether or not a rise in postsynaptic calcium was necessary to make synapses strong, they did the experiment they had done before in exactly the same way, except that they prevented intracellular calcium in the postsynaptic side from increasing. After they repeated the experiment, they found that indeed the synaptic strength remained entirely normal. That is, that increasing postsynaptic calcium is necessary to make synapses strong. Now, unfortunately, because the scientists only altered calcium, they concluded that it was in fact sufficient to make synapses strong. This is a big question. Is a rise in postsynaptic calcium sufficient to make synapses strong? And the experiments so far have not satisfied the conditions such that we can say whether or not it's sufficient. To answer the question of whether or not a rise in postsynaptic calcium is sufficient, we have to determine if the rise in postsynaptic calcium can make inactive synapses strong. You recall in the experiments up to now, they've always activated the synapses while they increased postsynaptic calcium. They then repeated the experiment they'd done exactly as they'd done before, except they did not activate the synapse while they increased the postsynaptic calcium. And after a series of repetitions, they found that indeed the synaptic strength remained exactly as it had been originally, that is, in a normal case. In other words, increasing postsynaptic calcium alone does not make synapses strong. Increasing postsynaptic calcium is not sufficient to make synapses strong. Synapses also have to be active during calcium increases in order to be made strong. Thus, other factors related to activity are also necessary. In conclusion, increasing postsynaptic calcium is necessary but not sufficient to make synapses strong. So we have this confusing situation where the scientists concluded that a rise in postsynaptic calcium was sufficient to strengthen synapses when it really wasn't. And we can ask the question in general, what do scientists mean when they say a condition is sufficient when in fact it is not? I think there are several things that are involved. For one thing, they might mean that compared to some more complicated conditions, the one that they're studying seems to be sufficient. They find that if they manipulate just one condition alone, then the phenomenon they're interested in is affected, and that condition then is sufficient to cause the effect as far as they know. They do not, of course, say that they've ruled out all other possibilities, since this would be impossible, and they use the word sufficient to make their results seem more important. However, saying that something is sufficient when it obviously isn't obscures the fact that deeper complexities will eventually emerge, and it causes needless confusion. The question is there a better way to proceed? And there is a better way. Rather than resorting to inaccurate and imprecise terms like sufficient to emphasize the importance of their results, scientists can simply state the hypothesis or hypotheses that they're testing, such as synapses become stronger after postsynaptic calcium concentrations increase. They can extract predictions from the hypothesis, such as preventing increases in postsynaptic calcium concentration will prevent synaptic strengthening. They can then test these predictions experimentally, that is, test the hypothesis, and finally they can explain their results, their reasoning, and the conclusions they arrive at. This method avoids the confusion that can be caused by the use of incorrect terms and makes for clear and precise communication, which is one of the major goals of science. Thanks for watching. Remember to give it a thumbs up if you like it and subscribe to hear more. See you next time.